Staphylococcus, gram-positive bacteria that lives with you and occasionally attacks you. It can cause anything from small pimples to pneumonia, sepsis, or even toxic shock syndrome. For decades, we've relied on antibiotics like penicillin to treat it. It works by attacking the bacterium's cell wall. But Staph evolved a clever countermeasure, an enzyme called beta-lactamase. Beta-lactamase destroys penicillin by cutting the drug's core structure, the beta-lactam ring, making the bacteria resistant. To fight back, scientists developed new beta-lactam drugs like methicillin. This new drug was designed to resist destruction by beta-lactamase. Some staph strains evolved a completely different strategy. They acquired a new gene, the mecha gene, which codes for a modified protein in their cell wall called PBP2A. PBP2A has a different shape than the normal target. When methicillin or oxacillin tries to bind, it cannot fit properly and slips off. As a result, the antibiotic cannot stop cell wall synthesis, and the bacteria survives. This is why these bacteria are called MRSA, methicillin-resistant S. aureus. For severe infections, doctors turn to vancomycin, a powerful antibiotic that targets the cell wall differently. Vancomycin is often the last resort against MRSA. Vancomycin stops bacterial cell wall formation by binding to the diala part of the cell wall precursor. This blocks transglycosylation, so the cell wall cannot be properly built, resulting in a weak and defective cell wall. But staph has shown it can resist even this. Some strains, known as VISA, vancomycin intermediate S. aureus, develop an extremely thickened cell wall. VISA strains of Staphylococcus aureus make extra, thick layers of peptidoglycan containing many diala units. Vancomycin binds to these outer diala sites and gets trapped there. This creates a barrier, so less vancomycin can move deeper into the cell wall to reach its actual target and stop cell wall synthesis. But the story does not end here. Beyond VISA, VRSA has emerged as an even more serious and evolving threat to modern antimicrobial therapy. Vancomycin-resistant Staphylococcus aureus. This resistance arises when S. aureus acquires the VANA gene from vancomycin-resistant enterococci, VRE. The VANA gene modifies the bacterial cell wall precursor from diala to diala-D-lac. The last diala residue has been replaced by a D-lactate, so vancomycin cannot bind. In the resistant bacteria, cross-links are successfully formed. Its emergence sends a clear warning: antibiotic resistance is no longer a distant concern, but a present danger, demanding strict antimicrobial stewardship and rigorous infection control measures. Stop the overuse of antibiotics. Every unnecessary dose fuels resistance.